Ma'am, this is Rajesh of CIC. Now I'm going to give a seminar on IR spectroscopy.
Good morning, one and all. This is Rajesh of CIC. Now I'm going to give a seminar on IR spectroscopy. Introduction to IR spectroscopy. In the year 1800, a German astronomer called Sir Frederick William discovered the part of the electromagnetic spectrum known as infrared region when he was observing the sun. IR spectroscopy is also called as vibrational rotational spectroscopy. It is also called as absorption spectroscopy because when the IR light is incident, the molecules in the compound absorb the energy and exhibit vibrational and rotational transitions. So it is a type of absorption spectroscopy and called as vibrational and rotational spectroscopy. Here is the diagram of electromagnetic spectrum, where IR ranges from a wavelength of 700 nanometer to 1 millimeter and a frequency of 430 terahertz to 300 gigahertz. Basic conditions for absorption of IR radiation. There must be a change in dipole moment of molecules as a result of molecular vibration or rotation. It should have resonant frequencies that are in the infrared frequency range of 100 to 4000 centimeter inverse. Coming to the principle behind IR spectroscopy. In any molecule, it is known that atoms or groups of atoms are connected by bonds. These bonds are like springs, not rigid in nature, and there is continuous movement in molecules. Because of this continuous motion of molecules, they maintain some vibrational and some frequency characteristics to every position of molecule. This is called natural frequency of vibration. If applied frequencies of IR is equal to natural frequency of vibration, then absorption of IR radiation takes place by atoms, and a peak is observed due to transition of higher energy level. Different functional groups absorb IR radiation, hence gives different peak values. Therefore, IR spectrum of chemical substance is a fingerprint of molecule for its determination. Coming to the IR region. We all know IR region comes after the visible light region, where it ranges from a wavelength of 700 nanometers to 1 millimeter and a frequency of 430 terahertz to 300 gigahertz. IR region is divided into three parts: near IR, mid IR, far IR. Here, mid IR region is special. It is called functional group region, as all functional group and molecule vibrations are identified in that region. Mid-IR ranges from 2.5 to 50 micrometer in wavelength and 4000 to 200 centimeters inverse in wave number. Coming to the instrumentation of IR spectroscopy. Let's say it requires two heads for vibration. So only two heads can vibrate it. First, as you can see in the diagram, when a beam of light from the source is split into two and passed through reference and sample respectively. Now both of these beams are reflected to pass through splitter and then through a detector. Finally, the required reading is printed out. This is the instrumentation of IR spectroscopy. Let's take formaldehyde and let's assume oxygen and carbon are in spherical shape. Okay. Coming to the vibrations, this up and down vibration is called stretching vibration. Okay. Now coming to wagging. This to and forth is called wagging. For example, in the formaldehyde, let's say for stretching vibration it requires two hertz. Okay, so when a light of 2 hertz is incident on it, it absorbs the light and exhibits stretching vibration as shown in the video. And coming to the wagging, let's say it requires 4 hertz. Okay, when a light of 4 hertz is incident on this, it exhibits wagging. So when this formaldehyde is kept in the IR spectrometer, where it needs 2 hertz for stretching and 4 hertz for wagging, this is the light source, and a detector is placed to detect the amount of light transmitted. Let's say 1 hertz of light is passed through the formaldehyde. It doesn't matches with the natural vibrational frequency, so there is no absorption takes place. And when we plot a graph against the amount of light transmitted and the frequency, at 1 hertz we get 100% of light detected because there is no absorption of light taken takes place. So when we pass at 2 hertz, it matches with the natural vibration frequency and a little amount of light is transmitted. Let's say this is the percentage of light transmitted. And next, let's take 3 hertz. It doesn't matches with the natural vibrational frequency, so the detector detects the light and the outcome is 100%. Okay, this is the graph. And let's say if we take 4 hertz of light, it does matches with the natural vibrational frequency, so a little amount of light is transmitted and detected by the detector. And let's say this is the amount of light transmitted and this is the graph. Okay, this is what the IR spectrometer prints out. A midair region. Midair region consists of functional group region and fingerprint region. Functional group, it ranges from 4000 to 1500 centimeter inverse. It takes stretching vibrations into functional group region. For example, C double bond C stretch from 1680 to 1640 centimeter inverse. CH stretch from 3100 to 3000 centimeter inverse. HC double bond O stretches from 2830 to 2695 centimeter inverse. These are the examples of functional group. Coming to the fingerprint region, it ranges from 1500 to 600 centimeter inverse, where bending vibrations are accommodated. For example, OH bent from 1440 to 1395, and it also bend from 950 to 910 centimeter inverse, and CH bent from 1000 to 650 centimeter inverse. These are the examples of fingerprint region. This fingerprint region is important because it gives a unique spectra for unknown compounds. Coming to the applications of IR spectroscopy. It is used to determine the type of group present in the compound, to study the covalent bonds in a molecule, to study the environment around the molecule, to find whether the conjugation is present or not. It is used in forensic analysis. In daily life, it is used to identify odor and taste. And it is used in biomedical study of human hair to determine the atmospheric pollutants released from industries. And yeah, no two samples will have identical IR spectra.